Now you're gonna be YouTube famous.
Wait, why?
I put him in a video. Especially before. Watch after the first test. After we get back the first test.
Is it like half or gone or something?
All right.
More.
So you guys got in homework number 4 over the weekend. Solutions went up. That puts everything in your hands that you need to prepare for the exam that's coming up this Wednesday. Remember, that happens during the lab period, but it does not happen in the lab room because we have a little bit of a space issue. So don't forget. I'll try to remember to put signs on the lab doors in case you forget that you're supposed to be going somewhere else, or if you remember that, where you don't remember where that is exactly. So, but do remember that we're going to be holding the exams in a slightly different location than usual. Other than that, Pio, where's Pio? So you are going to be doing some exam review in the SI session today, yes? Okay, so if you are interested in some exam review and you're not already a regular attendee, hit up Pio on your way out, and you can get the details on that. Other than that, life moves on. It's not just all about the exam. We're going to continue to accumulate a body of material here so that we can have another homework on circuits, homework 5 ready to drop. You'll have about a week to do it following the exam, but I want to get that material in your hands. Okay, any quick administrative or logistical questions before I jump in? Okay, so Ohm's law right here. We talked about this last time. In circuits, when we say V, we really mean the voltage difference between 2 different locations. And if you apply a voltage difference across 2 different locations, that provides motivation for charges to go because they can lower their potential energy. And so we will get the amount of current, and the amount of current depends on also on how much inherent resistance is in the way of the flow. So current, that's the charge that flows per time. The units are coulombs per second, that's amps. And resistance, as we found out, how difficult it is to move through a particular type of obstruction can be determined by the physical characteristics of what it's made out of. So if we have some sort of cylindrically shaped or some kind of something like that, then it depends on the length that the charges have to get through. It depends on the cross-sectional area that the flow has to go across. And then the final variable there is rho, not to be confused with the charge per unit volume, which is what we've been using it for in homeworks 1 through 4. But this is called the resistivity. It's measured in ohm meters. So that's the inherent property of the material that informs how resistive and often, or not resistive something is, and oftentimes that factor is far more important than the physical dimensions. If you're talking about resistors, chances are they're about this long, not about this long, okay? And if you're talking cross-sectional area, it's not like this huge. But the resistivities can vary by gigantic orders of magnitude. And so you can have something that is far, far, far longer than something else, but still lower resistance because of what it's made out of. As I talked about last time, this can really have a range anywhere from 0 up to infinity. And at some point, we sort of make an arbitrary break and call things below that conductors and things above that insulators, even though there's no fine line. So for instance, in circuits, we often take the conductors, the wires themselves, as having no resistivity, even though they do have some. It's just minimal compared to these special resistors that are in the way, which have a far higher resistance value. So these might be like your wires, and these might be like your special resistors. So there's one more thing, actually 2 more small things I need to do before we just get to building some circuits. The first of all is that resistivity, it depends on the physical construction, but there are ways you can manipulate what the physical properties are, and I'm not going to look at all of them, but one I am going to look at is temperature. So resistivity depends on temperature. Okay? So if you guys may remember, you took a 30-foot wire coil and you did several different measurements on its resistance, one when it was around room temp and one when it was around 70 degrees. Remember this? Okay. And so you showed that you can change the resistivity and therefore you will change the resistance of that coil. Okay? So let me give you the function first. The function looks something like this. I guess let me write out delta T. Delta T is T minus T naught. So, first of all, if you were to plot the resistivity versus temperature, first of all, there's a baseline. The baseline is that at a certain T naught, you start off with a known resistor, rho naught. Okay? So oftentimes T naught is said to be room temp, 20 degrees Celsius. And for instance, you can find on the equation sheet, it's on the third page in the lower left, lower right corner, you can find a table of what is the quote-unquote standard resistivity at that reference temperature. So that's your starting point. That's your baseline. But then, if you do change the temperature, you will change the resistance. So for instance, maybe it looks something like this. Now you can actually put this thing into point slope form, and you will find that the slope here is alpha times rho naught. Okay? Now, let me give you a little bit of a sense of where this comes from. This comes from the fact that an engineer got in the lab and measured some data, and it looked linear. And guess what? Anything looks linear if you zoom in far enough. Okay? So who knows what this function looks like later on? But as a small, subtle refinement, everything looks linear. And this thing here is called the temperature coefficient of resistivity. By the way, if you ever hear anybody call something coefficient of blah blah blah, you can bet it's experimentally determined by data. That includes coefficient of friction, coefficient of thermal expansion, for those of you guys that took Physics 270. Anything coefficient of blah 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 is always just an experimentally determined value. Okay? So in my case, I've drawn a positive temperature coefficient because the slope is obviously positive. It is also possible that when you increase the temperature, the resistivity drops, and who knows what the actual function is, but if you zoom in far enough, it's going to look linear, and so this is just the linear approximation of whatever more complicated model might be there. Okay? So this would indicate a negative coefficient. Now I'm going to give you a little bit of insight as to why some materials might have positive versus negative temperature coefficients. There are two factors at play when you increase the temperature. So when you increase the temperature of a material, one of the things that you do is you make the atoms wiggle around more, right? That's what a higher temperature is, right? So what happens is that the atoms wiggle around more, and if the atoms are wiggling around more, then the electrons have a harder time getting around it, right? Is it easier to walk through a crowded room if it's a dinner party or a mosh pit, right? So if everyone's kind of flying around, then it's hard to get around. And so if this is the case, what would you expect that to do to the resistance?
Increase it.
Increase it. It would tend to increase the resistivity and therefore increase the resistance. So these are harder to get around. Okay? Think about the dinner party versus the mosh pit example if that doesn't help, okay? But there's another factor, and this is the shaggy dog analogy, okay? So if a dog is coming out in from the rain and it shakes a little bit, it's not going to get much water off, right? So it has to shake very vigorously to get all that water off, right? Well, that's exactly what can happen to an atom. If you shake it really hard, it'll actually spray off electrons. It'll actually lose electrons. And that's more electrons that would contribute to the flow, okay? So the second factor is that the atoms actually throw off previously bound electrons. So now you've got more electrons joining the party. So that's going to make the flow harder or easier?
Easier.
Easier, right? So you're not just a few electrons trying to bob and weave. You're going through the dinner party and everyone's saying, hey, where are you going? I'll come with you, right? So then you have an easier time. So that's going to lower the resistivity and lower the resistance. So what you have are two competing factors, and which one matters more is going to overall determine what happens to the resistance. So if I call this factor A and I call this factor B, the positive ones, they're A dominated. So A matters more than B, and the negative ones are more B dominated. Okay? It's just which factor ends up being more important. Okay? So just to give you an idea of typical materials, ones that generally tend to have their resistance go up, these are things like metals. That's what your coil was, by the way. It was a copper coil. It had some insulation around it, but it was basically a metal. The reason why this is true with metals is that metals already have plenty of free electrons. But, so, the throwing off more electrons to join the party, you've already got plenty. But the atoms that are there wiggle around more, and they are harder to get around. The ones that have negative temperature coefficients, where the resistance actually decreases with temperature, that's an important class of materials called semiconductors. So these are things which don't really like to have electrical flow happen, but if you increase the temperature, you can actually encourage the flow, whereas before the resistance was higher, you're increasing the temperature and it's lowering the resistance. Okay? So that's an important class of materials. It's materials that are sort of just on this side. Oh, sorry, wrong side. Just on this side, they're insulators, and then you coax them a little bit, and they actually become pretty good conductors. So, silicon, germanium, those are the two major ones. Both the first computer chips ever were made out of germanium, and then they decided that that was for other reasons they didn't do that. Now they make them out of silicon. Okay? So silicon is one of the things that has a negative temperature coefficient, and that's a good thing, because you can coax it with not too much effort. The atoms can throw off previously bound electrons, and it becomes something where electricity can flow more easily. Okay? So that's just a little bit of how you can literally modify the physical properties, literally with heat, and you can modify the resistivity, and therefore you can modify the resistance. Okay? Are there any questions on that? Okay, so the final order of business, before we just start building circuits, is we've already mentioned that when you have electrons burrowing through these wires, we said that the potential energy does not get kept as kinetic energy, at least of the charge itself. This is not flying through free space. You should be, of course, very competent with K plus U conservation for the exam on Wednesday. But in this case, it's not moving through free space. It goes to thermokinetic energy. And the one thing that we have yet to mention is, okay, how can we quantify that? Okay? So, let me attempt to do that. Okay? So, we can take this formula right here. The amount of potential energy that you lose is determined by the charge and then the voltage difference that it goes across, right? So if this is delta V and this is Q, when Q moves across that voltage difference, that's how much potential energy it will change, right? Is that okay so far?
Mm-hmm.
It's going from U equals QV. I just did it with the delta form. Is that okay if I jump to that? Okay. So, that right there is not an interesting question because, of course, the longer you let the charges go through, it's not just one, it's many. There are a bunch flowing through. And the amount of energy that's going to be released is just more over time, right? So this keeps on happening. So this one charge comes through, converts this, then another one does, and another one does. So it's much more interesting to talk about the rate at which it happens, right? Instead of just talking about the total amount. It's like having a light bulb and asking how much energy did that light bulb release? It really just depends on how long did you have the light switch on, right? That's not an interesting question. What's more interesting is the rate at which it releases energy. So what I'm going to do is I'm going to define the power, which is, of course, energy conversion per time. Okay? So for those of you that may not remember, the units of power are joules per second, and that's called a watt. So why, for instance, is a 100-watt light bulb brighter than a 50-watt light bulb? Well, a 100-watt light bulb, what does that really mean? A 100-watt light bulb is what that's saying is it converts 100 joules of energy from electrical to heat and light per second. That's what 100 watts means. Really, for our old school normal, well, not normal anymore, they're illegal in California, the kind of light bulbs I grew up with, the incandescent light bulbs, they literally just get so hot that they happen to glow, okay? In fact, about 90% of the energy goes to waste. You're lucky to get 10% out, which is why they're illegal, by the way, because they're highly inefficient. You know that they get hot. If you ever reach into a light socket and try to take one out, you will burn yourself. That's how you find out that's an old incandescent light bulb and not one of the new CFLs, okay? So most of it is byproduct, most of it is heat. So out of that 100 watts, 90 watts goes into this, about 10 watts goes into that, if you're lucky. That's all well and good if you are also trying to warm the room. Okay, if you have a bad heating system and it's cold out, you can turn on all your incandescent light bulbs and they serve as heaters quite well. Okay, but if you also have the air conditioning on, it's total waste. And that's why they have CFLs now. So you can now buy a 10 watt that's just as bright as a 100 watt. And old timers like me get confused when they go to the store. I'm like, 10 watts, this thing is going to be so dim. And then you have to read the fine print. As bright as the old 100 watt bulbs, old timer. Okay? So my intuition is totally off because I grew up thinking 100 watts is like this, 50 watts is like this, and now it's all changed. Okay? So that's basically a little bit of review. Of course, in Physics 1, you may have talked about watts primarily in terms of conversion of one mechanical energy to another, but of course, it's any energy conversion per time. The energy can go from any form to any other form. So in this case, it goes from electrical to heat and light. So what do we got? Over here, I'm going to group the charge per time, and that's current. And then delta V, of course, I shouldn't be calling it delta V because I decided to call it V, so there I have it. There's my formula for how much power is dissipated in a light bulb. And I call it dissipated because, of course, it's going from a more useful form, like electrical, into a form that's sort of more diffuse, like heat, okay? If you want, you can think of it like this. This current, what is current? Current is charge that flows per time. That's what the definition of current is. And then voltage, this is something you should know. Voltage is joules per coulomb. So this is energy per charge. So this is energy lost per charge. Okay? A volt is a joule per coulomb. Now if you notice here, the charges are just the middleman, but what you do have is energy lost per time. And again, when I say loss, I mean as heat. It doesn't get destroyed from the universe, of course. Okay? So it is just energy per time. The charge is just the middleman for that, right? It's like if you want to know how much mail is delivered every day in the US, right? You'd have to take how much mail is carried by each mailman, mail carrier, and then how many mail carriers go out every day, right? You can multiply the two, and you could get that, right? The mailmen are just the, postal workers are just the intermediary, right? So that's what's happening here. The charge is just an intermediary. It's how many charges you have per time, and how much energy do they each lose, okay? And the multiplication of those two just gives you the total energy loss per time to heat. So that's my formula for the power law, and I'm going to give myself some options. So I have Ohm's law, and I can sub in. For instance, I can sub in for V, and I get I times R, so I squared R. Or I can choose to instead sub out the current. So I can plug in for the current instead, and that will give me this. So there's three different options for the power law. Basically, you have three ingredients, I, V, and R, and we have each of the two of them pairing up while the third one takes a breather. So you have three different forms. Now you might question, why would we want to have three forms sitting around? There's going to be good reason when we move into more complicated circuits to have choices. And we'll find that some of those power laws are really helpful for some types of circuits, and other ones are helpful for other circuits, so it's nice to have them just ready-made so we can grab at any one of the three that's convenient. They're all equivalent, they all come from this, but I'm subbing in Ohm's law to get the various different options, okay? So that should be everything I need to start building circuits. I have my Ohm's law itself. Of course, I want to understand what current and resistance are, and then I have the power law. Okay, are there any questions before I make a circuit? All right, so let's start building circuits. Let's see how many we can do today. So this is going to be very, very simple. I'll call it a simple circuit. It's going to be perhaps painfully easy, and it's just going to give me an opportunity to give you various symbols and things like that. The actual calculations are ridiculously straightforward. And let me pull out my thing just so that I use the values that I want to. Okay, so first, I have a battery. This is a symbol for a battery. So what these represent are two equipotentials that are at different voltages from each other, and you represent schematically that the higher voltage terminal of the battery is the longer plate. So this is the higher voltage. And this one is the lower voltage. So the battery is something that gives us a voltage difference to play around with. As far as how these are internally constructed, that I'm going to have to leave to your Gen Chem class. Basically, there's a chemical reaction running inside it. But for us, the battery is just a thing that somehow is able to maintain a voltage difference that we can then utilize. Other ways that these plates are notated, oftentimes the higher voltage is colored red and the lower voltage is colored black. Again, you don't have to paint it that way, but it often is. You can paint them purple and brown or whatever if you feel like it, but no one will look at that and know what you're doing. That's the point of conventions, right? Oftentimes, the higher voltage terminal is labeled plus, and the lower voltage is labeled minus. That one particularly bothers me because there is no reason that they would have to be labeled that way. Why not label this one plus and this one plus plus? Okay? That's higher voltage, right? Why not label this as 0 and this is minus? There's no difference. That was one of the homework problems you may remember from homework 2, I think it was. I asked, what are the possible signs of these plates in order to get this potential difference? And the answer was basically all of them, right? It doesn't matter. Okay? So, no one uses these, so I'll cross them out. But there's your battery. Then we're going to hook up some wires. And then we're going to put something in the way. Here is our resistor. The resistor is not actually shaped like a zigzag like that. That is a schematic symbol to represent the bouncy path that charges take through it. Okay? Most oftentimes, it's really might be look something like this. You guys have already seen resistors in lab. They're not zigzag shaped. Okay. And in my case, let me give some values. Let me say that this is a 12-volt battery, and I'm going to give a special symbol for the voltage across the battery terminals. This is called EMF. It's a special character reserved for when you're not talking about any old voltage difference, but the voltage difference across the terminals of the battery. EMF is an acronym. I don't want to tell you what it's for because it's, well, I'll tell you, it's electromotive force. It's not a force. It's one of those things that someone really should have fixed that once they figured out what was going on. Okay? So just call it EMF. And let's say that this resistor has an obstruction of, let's do 1 ohm. Okay. And I'm going to just do the basic calculations on this. How much current flows in this circuit, and what is the power dissipated in the resistor? All right. So, first things first. Remember that when we have these circuits, we have to think that there are special resistors, that's where all the resistance is, and then the wires, we're basically assuming that they're perfect conductors and that they add a negligible amount of resistance themselves. Now that isn't quite true because these aren't superconducting wires, but it's a negligible amount. And so what that means is that this equipotential is extended all the way over here. This is all one voltage plateau. That whole thing is an equipotential. It is all one contiguous piece of conductor. The fact that I stuck a wire on it just extends that somewhere else so that I don't have to put everything right on the battery. And same thing over here. This whole thing we take to be an equipotential as well. So if I connect to the terminal of the battery an ideal wire, we assume that there's no voltage drop across an ideal conductor, and therefore all of the voltage drop occurs across here. Okay? So going from here to here is a 12-volt drop. All of the voltage drops across that resistive element. That is what separates the two plateaus from each other. Okay? So this region is 12 volts higher than here, okay? So, now we know the motivation of charges to go through that obstruction, and we also know how much resistance is in the way. We can solve for the current. So, very straightforward, just 12 volts divided by 1 ohm, we get 12 amps, okay? So 12 amps, or 12 coulombs per second. That is a dangerous amount of current, but I wanted to use nice round numbers, okay? Now, let me talk a little bit about the nature of the current. This is where students get a little bit in trouble, I've found, because they think of this as like an empty garden hose when you turn on the tap. This is not an empty garden hose, it is actually a full garden hose. So you have to think of it as this entire system is already filled with electrons, okay, everywhere.
And you're just motivating.
Man, I shouldn't have drawn this many, but they are already everywhere, okay? They pervade the entire system. And when you connect the battery, they will immediately sense throughout the system, the message travels basically at the speed of light, that it's open for business, okay? So the whole thing starts moving like this. So think of it as the entire system is filled already, and now they just have some desire to move. So the analogy I will give is you have a bunch of people waiting in line for auditioning for American Idol. That's not even on the air anymore. I'm really need to update my analogies. You guys still know what American Idol is, right? Okay. So you have like what, 500 people waiting in line, right? Okay. Once they open the doors in the morning, it can take you hours for you to get in there, right? But how long do you think it's going to take for you to hear that the door's open?
Instantly.
Almost instantly, right? Everyone's whispering it down the line, right? That's what happens here. Now, when you flip this light switch, and the electron that goes through the light switch at that moment, that goes right through the connection that you just opened up, or that you just allowed, it can take minutes for that electron to get to the light fixture. Minutes. And yet it turns on right away. Why is that? Because there were already electrons in the light fixture, and when you hit the switch, they heard, and they started moving. Okay? Does that make sense? Okay? So the entire system is filled. And the amazing part is that these electrons will detect just how much resistance is in the entire path. In this case, 1 ohm. And they will all start moving at 12 amps, or at 12 coulombs per second. So if you put in a roadblock here, or here, or here, or here, right, and you asked how many coulombs pass per second, the answer at every single every single stop there would be 12 coulombs pass per second. There's a nice orderly flow. There's not any of the surging and then, oh wait, we have to wait for this guys to clear out. It's a nice orderly thing. And that is determined by how much resistance is sensed in the entire path. Okay? Does that make sense?
Professor?
Yeah.
If you put the red and dark one on just one side of the equipotential, it's just gonna give you that reading, right? Would just give you 0. There's no voltage difference, right?
Right, so if you
Okay.
pushed it here and here, this whole thing is an equipotential, so you would get just 0. That's
Okay.
right. The only way you would get any reading in this circuit is if you connected somewhere between this region and this region. That could be here and here, you get 12 volts. You'd be here and here, get 12 volts, here and here, 12 volts, 12 volts, 12 volts, 12 volts, 12 volts, 12 volts, 12 volts. Okay? It's just like there's 2 levels. Okay? Does that make sense?
Yes, sir.
So one of the things that you might I do sometimes is I'll label this as equipotential A and this as equipotential B, and then I'll make what's called a voltage waterfall. And the rules for this is that if you're higher on the page, that's higher voltage. So I always like to orient vertically because I'm always tied back to gravity, right? Higher on the page. And so that looks like this. So there's the battery, and there's the resistor. That's the amount that drops to the resistor. So you can think of it basically as charges cycling between two equipotentials. Oh, and before I even do that, I forgot to mention, of course here I drew the actual electrons. Electrons like to go to higher voltage, but remember when we talk about electric current, we take electric current is the hypothetical flow of positive charges to lower voltage. So we pretend with just Ben Franklin's old stupid mistake is that the current flows like this. Okay? So what you can think of as going in this system, it's kind of like a fish tank, okay? These positive charges go down, and then the battery basically acts like a pump to get it back up. So they circle around like this. The battery essentially acts like a pump. When positive charges go in here, they will pop back out here, but at a higher voltage. And then they will continue down, okay? Any questions on that? Okay, so let's knock out the power here, of course, as well. The power, I have any number of choices there. It doesn't really matter. This circuit is so simple. There's no real advantage for choosing any one of the three forms of the power law. We just pick one. I guess let's choose the first one, I times V. So that would be the current we found was 12 amps. I guess the compelling reason to use the last one is that it's using given information, just in case we calculate the current wrong. So, but I'm already using this one, so let's use that. So 12 amps, and the voltage is 12, so that's 144 watts, okay? So, if this were a light bulb that would sufficiently heat up by releasing 140 full joules per second, this could be a light bulb filament, okay? I guess let's see it in action. So here's what I have.
Nice.
I have a car battery charger. If you're wondering why I brought a machine gun to a fist fight, I'll explain that later, okay? This can output 350 amps, okay? This is serious business. I will explain why I'm using this later. And then what I have here, I have these two metal prongs, only purpose of which is to raise this up a little bit so that people in the back can see. You can see that this clip is red, that's the higher voltage. This clip is black, that's the lower voltage. And essentially when I clip it to these poles, these are conductors, so this is just extends the equipotential. So this is the higher voltage, and this is the lower voltage. Okay, so I take a resistor, this being a light bulb, I connect it across, and I, actually, do I want to do that one? What order do I want to do these? Yeah, sure, let's do this one first. So I turn on the juice here, and we have light, okay? You've seen a light bulb before, okay? So this whole region here, okay, everything before the light bulb filament, okay, that's the higher voltage plateau, that's here. And then everything after is the lower voltage, okay? So the voltage drop is basically just happening across the light bulb itself, okay? Question?
So if you touch the prongs,
yeah.
you like get electrocuted? Or?
If I touch these?
Yeah.
Well, I wouldn't because this is a far easier path, right? So I don't have as much resistance, but that's not something you want to also mess around with because it might not be 350 amps, but it still might be enough to kill you because 350 amps can kill you several times over. Okay?
Holy shit.
So I'll tell you why I'm using that a little bit later. It's because I need something that acts more or less like an ideal source. Okay. Okay. So the only other thing that I wanted to do with this simple circuit was to just suppose to you a hypothetical question let me copy the circuit I have here that I just did for reference. So I had a 12-volt battery and a 1 ohm resistor. Yes, yeah, 1 ohm. And I calculated that the current was 12 amps and the power was 144 watts. Okay. So now, I'm going to use the same battery, 12-volt battery, but I'm going to put in a resistance that's twice as much. So same motivation to get across that. Okay. So 12 volts reward if a positive charge is willing to burrow through this obstruction. Okay, so the reward is the same. However, the obstruction has become larger. So do we expect a larger current or a tiny trickle of current? Is it going to be more current or less current than before?
Less current.
Less current, that's right. You can see I equals V over R. If we're fixing this, if we increase the resistance, we should have a drop in current. And in fact, because it happens to be twice the resistance, it's going to be how many times the current?
Half.
Half. Proportionality. Yep, it keeps on giving. And we find, you can try it yourself if you don't believe me, the current is indeed less. Okay? So then, we look at the power. So again, the voltage is fixed. So remember what voltage is? This is the energy lost per charge. So every charge, every electron that flows through that resistor, or if you want to think of it as hypothetical pretend positive charge carriers, okay? Every single charge carrier that goes across there still loses the same amount of energy, but you just don't have as many of them, right? So if the current is less, so there's the charge per time, there's not as many charges flowing through per time. So what's going to happen to the power?
Goes down.
It drops. And since they're directly proportional, that's going to just current half, so the power is going to be halved, right? So, something I want to point out to you is this. A brighter light bulb has a lower resistance, okay? It puts less in the way of the flow, so a lot more flow will rush through it. The other extreme is you put an infinite resistance, right? Then what's the flow? How much can get through an infinite resistance? 0, right? So that's when nothing will happen, okay? The reason why I did these two is because these are the very same two resistors that I will now be putting in together. So not one and then the other. I want to build circuits with the same battery and the same two resistors, but actually connected together in various ways, okay? So let me do, I don't know if I'm going to be able to finish this, but I'm going to start it today. This is the series circuit. So looks like I'm going to start series today, but Wednesday morning is going to be the lecture where I finish series and talk about parallel. It happens to fall the morning of the exam. I would strongly recommend that you not skip that because it's a cornerstone of the entire next homework and the lab that you will do next week. Okay? So again, life goes on. Don't pull an all-nighter Wednesday morning. You're not going to want to miss that. Okay? So series circuit. I'm going to take my 12 volt, my 1 ohm, and my 2 ohm, and I'm going to connect them in a row. Like this. And what we want to do, our goal is, what is the current for each one? What's the voltage for each one? and the power for each one. And in anticipation of coming up with a bunch of different relationships, I'm going to start a table so I can keep track of the results. So series, and this is to be contrasted with another way to hook these guys up, which is in parallel, okay? So first of all, I'm going to look at, and this is generally good form, is to circle your equipotential regions. So this right here is the highest voltage in the circuit. That's equipotential plateau 8. How do I know that? It's of course connected to the higher voltage terminal of the battery. There is also one here. And remember, the wire just helps to extend it. And that is the lowest voltage in the entire circuit. The battery terminal is set at the top and the bottom. But in this circuit, there is also one more middle step right here. I'll call that B. I saved the letters so I can label them in order. So B is somewhere, it's lower than A but higher than C. Now how do I know that? Well, remember that the entire system is filled with charge carriers, and they will sense how much is in the way and will flow accordingly. So there will be a current that flows throughout, so on and so forth. And that current will be the same thing. So this is especially important now to remember. This is not like an empty garden hose where suddenly the charge rushes through R1 and then says, oh, I didn't know this was coming, and slows down. The flow is established by sensing the entire resistance in the way, and in fact, in series, the current is the same in each resistor. And that's because there are no forks. There's nowhere else for the current to go. There is one path through the circuit, and the amount of current that will flow is established by that, okay? And so, if current, remember current is made out of positive charges, so if you want a charge to go through, you have to offer lower voltage. So B must be lower than A. So charges will flow from A to B, not because you want them to, but because they have an energy reward. They go to lower voltage. But they would not continue to flow if there were not more lower voltage available. So B also has to be higher than C. That's what keeps the charge continuing to flow. Okay? Current seeks lower voltage. So if I were going to make my voltage waterfall, it would look like this. V1, V2. So this is like a waterfall with a middle stop. It's like two waterfalls stacked on top of each other. So you drop some of the voltage going across one, and some of the voltage going across the other. Okay? And then the battery just pumps it back up again to go all over, to happen all over again. And one of the things you notice here is that, of course, the sum of those two voltage drops is just your battery voltage. Okay? Your journey from top to bottom will just take you 12 volts lower than you started. It's just that it happens in two increments. Now you might ask, isn't it just 6 volts and 6 volts? Well, no, it's not. Okay? The voltage generally is not the same in series. Voltage is not the same. Okay? So, let's pick up there on Wednesday morning. We'll finish this.